Hey guys, so today we're going to look at compound inequalities. Now, we looked at, I guess, what you would call a normal inequality first that had one solution set. It usually started at a number and had all of the solutions above or below that number. Now, compound inequalities are a little different. So when we're looking at compound inequalities, so think about, what does compound mean? Well, compound, you're usually putting two things together. So these look a little different at first. First thing I notice, well, I've got two inequality signs. Well, that makes sense. Compound, we're putting stuff together. So there's a couple different ways that you can solve this. I like to think about it how we put our lines down when we're solving our equations to keep everything equivalent. Well, notice, I don't just have two sides, I have three sides. So our whole goal still remains the same. Isolate our variable. So if we're going to isolate x, so I'm just focused on the middle. So 7 times x minus 13. Okay, so I need to undo a multiplication and I need to undo a subtraction. So I'm going to use PEMDAS in reverse and start with my addition and subtraction. So I've got minus 13, so the inverse plus 13. So now, notice, I'm adding 13, so I have to do it to every side. So that's what makes this a little bit different, because I not only have one inequality, I have two. So I'm going to add to both sides. So 8 and 13. I'm just bringing down the inequality signs. Negative 27 plus 13. More negative, so it stays negative, negative 14, and just bring down our 7x, or 7 times x. So, getting rid of the 7 times x, I'm going to do division. So I'm going to divide both sides by 7. Well, all sides, not both sides. Divide all sides by 7. So x is less than, I divided by a positive, so I don't have to mess with my inequality signs. So x is less than 3, but x is also greater than negative 2. So I have a compound inequality, meaning I have two inequalities. So it tells me another way to read this is that x is between negative 2 and 3. Now I want to think about inclusive or exclusive. So that negative 2, is that included in my solution set? Well, it's all about the inequality sign. Is it equal to? Nope. So our negative 2 stays open. How about the 3? Open or closed? Less than, so it stays open. And x is between negative 2 and 3. It's less than 3, so less than 3, but greater than negative 2. So our solution set is everything between those two numbers. Now, would negative 2 make this true? Plug it in. 7 times negative 2. Negative 14 minus 13. So negative 14 minus 13, it gives me negative 27. Is negative 27 greater than negative 27? No, it is not. It is less than 8, but it has to satisfy both pieces of the inequality. So that's why that is not included. However, if I plugged in negative 2, let's say 0.1, that would make a true statement. Now, interval notation. Notice this is a little bit different than we just had a single inequality. Nothing's going to infinity here. So when I set up my my interval notation, starting from smallest to largest, so when I come from the left, I start at negative 2 and I stop at 3. And think about open or closed. So negative 2, it is not included, it is excluded, so parenthesis. Same thing, 3 is also open, so it is a parenthesis. So this interval notation is looking a little bit different than before because we don't have anything headed to infinity. So a compound inequality can have a smaller solution set. Doesn't have to, but it can. All right, let's look at the next one. 7x minus 14 is greater than or equal to 0, or 4x plus 5 is less than or equal to negative 3. All right, so this is also a compound inequality. It just looks a little bit different because I'm saying I have this inequality or this inequality. So we're going to solve them individually. So 7x minus 14 is greater than or equal to 0. Okay, so let's go ahead and start there. 7 times x minus 14, so I'm going to add 14. So 7x is greater than or equal to 14, and then I'm going to divide by 7. So x is greater than or equal to 2. All right. This is just part of our solution, because remember it says or. So let's solve the other inequality. 4x, 4 times x plus 5 is less than or equal to negative 3. So I'm going to cancel out this positive 5. So the inverse is negative 5 or minus 5. So 4x is less than or equal to negative 8. All right, cool beans. Let's go ahead and cancel out that 4. So I'm going to divide both sides by 4. So x is, I'm dividing by a positive. Yes, there's a negative, but we're dividing by a positive, so no need to flip. So x is less than or equal to negative 2. Okay, so we have two solution sets. So let's go ahead and graph them one at a time. So x is greater than or equal to 2. So where am I starting? 2. And it is the equal to, so I shade in my bubble. And x is greater, so my numbers the greater are to the right. Okay. Now we also have x is less than or equal to negative 2. So again, where do I start? Negative 2. Equal to, so I shade it in. And where are all of the x's less than negative 2? To the left. So notice, look at the difference between the two solution sets of these inequalities. So who's bigger? This solution set only goes from negative 2 to 3, but this solution set, because it's an or, I only have to find a solution that satisfies one of the inequalities or the other. So I have a lot more to choose from because I only have to satisfy one of them. So when I write it in interval notation, so let's go smallest to largest. So where is this inequality heading? Left. So what does that mean? In the negative direction forever. So we're heading to negative infinity. And where do we stop? Negative 2. So remember, infinity is always open, so it's always a parenthesis, but negative 2, is this inclusive or exclusive this time? The negative 2 is included, so I need to use a bracket. So our other one, our other solution set, so we have a break here, and our other solution set starts at 2 and goes to where? Positive infinity. So infinity always gets parenthesis. That 2 is closed, so it gets a bracket. All right, now when you have two solution sets, you unite them with a U. Maybe. There it goes. Okay, so that's how we unite them with a U. That is a union symbol. So notice, this right here, I'm going to come up because my essential question, how do you explain the difference between and or in a compound inequality? Well, this first example is an and. This solution set is between negative 2 and 3, so it is a smaller solution set. Whereas if we have an or, I only have to be a solution of one inequality or the other. So that opens up the possible solutions a lot because we don't have to satisfy both pieces of the inequality like here. We only have to satisfy one or the other. Hopefully that makes sense. All right, so when I look at this one, this looks like an and. So I'm going to go ahead and solve. So looking at 2 times the quantity x minus 6, what do I want to do first? All right, normally we distribute. So I'm going to go ahead and distribute. Yes, there is more than one way to simplify this, absolutely. So I have 2x minus 12. Everything else is staying the same, so I just bring it down. And now isolate our variable. So get x by itself. So 2 times x minus 12. So I'm going to undo that subtraction first. So I'm going to add 12 to each piece. So here you see I find it really important to use those lines to make sure I do it to each piece and I don't just accidentally do it to one side but not the other. All right, so we still have 2x and less than or equal to 4 plus 12 gives me 16. And 2x is greater than negative 2 plus 12, so 10. And when I divide everything by 2, I get x is less than or equal to 8 and greater than 5. All right. So let's go ahead and graph. Feel free to pause the video at any time if you want to try it on your own and then check your answer. So x is between 5 and 8. All right, so at 8, I have an less than or equal to, so I'm going to close my dot. At 5, I have a less than, so there's no equal to, so that one's going to stay open. And x is between 8 and 5, less than 8, greater than 5, so I shade in the middle. So when I write an interval notation, my smallest solution is 5. My larger solution is 8. So I go from 5 to 8. Now, 5, open or close? Open. So it is exclusive. It doesn't include the 5. And 8 is inclusive, so we use our bracket. So again, notice these two examples are examples of and, because the solution has to be between this and that, between two numbers, whereas if it's an or, it can satisfy either parts of the inequality. It doesn't have to be both. I do want to bring up that compound inequalities, if they're an and problem could be broken up like an or problem. It just might say like one inequality and another. So the solution set when you solve it should still look like this. They should still go toward each other because it's just between the two numbers. All right, write an inequality that represents the test scores of 60% of his students. Okay, so what is it talking about? So Mr. Simonazzi knows that 60% of his students will score no more than 5 points above or below the class average, a 75, on the test. All right, so what are we talking about here? Well, we're talking about a test, and 60% of his students will score no more than 5 points above or below the class, so no more than the class average of a 75%. All right, so we're talking about a test, right? So no more than 5 points above or below the average. All right, let's think about this. So T is less than or equal to, so what's the maximum score of the 60% that the students can score? So if we're starting at, our average is a 75, what's the max? Well, 5 points above would be an 80. And then what would be the minimum? 5 points below that 75 would be a 70. So 60% of his students are scoring between a 70 and an 80. Is that included? I wrote equal to, but I want to make sure. So no more than 5 points above. So can they get the 5 points above? No more than 5. But yeah, they can get the 5. Okay, so it's going to be equal to. And then, or 5 points below. So again, no more than. So it can be that number. So same thing, less than, it can be that number. Okay, cool. So the test scores are between 70 and 80. That's all it wanted, us to just set up an inequality of what represents just the 60% of his students. So I do want to talk about inclusive versus exclusive. So inclusive, well, it includes, and exclusive excludes. So inclusive, that's when we have less than or equal to or greater than or equal to. Whenever we have those, that tells us that if we're graphing on a number line, what do we use? A closed circle. And then what else? Oh, when we're writing an interval notation. If something is inclusive, we use the brackets. Now, exclusive, that's our less than or greater than. So when graphing on a number line, we represent it using the open circle, and then we also denote it using parentheses. So inclusive and exclusive, those are words that you definitely might see in a real-world scenario. All right, hope that makes sense. You guys have a great day. I'll take any questions in class.